Hello, class. This is statics, week 4, Wednesday lecture. We're going to be doing just one problem today, and that is a three-dimensional particle problem. And the best way to explain the 3D problem is to simply work one. And that's what we're going to do today. We're going to work an example. The example is posted in Canvas, the problem itself, and then I also posted these notes that I'm going to go through are also listed on Canvas. It would help perhaps if you copied that problem and had it to look at. I will use the cam to help us along, but we want to stop the video and copy that. That might help you a little bit, but if not, we'll go through the at least part of the example. I think you'll catch on with what we're doing with the notes that you're taking. Okay, so I'm going to go ahead and share the screen. And this is the problem that we'll be looking at. And it's a cable, and it's subjected to a tension of 700 newtons. And this is cable AB. So we have cable AB here. We have also cable AC, and then we have cable AD, which we don't know the force in. And then there is a force directed up this pole, vertical pole, and that force is F, and it's directed along the Z-axis. And so the problem is, if AB, this cable has a tension force of 700 newtons, we want to know the tension in cables AC, AD, and F, which is directed along the Z-axis. So we have three unknowns. We have three equations. Sum of forces in the X equals 0, sum of forces in the Y equals 0, and sum of forces in the Z equals 0. So what we want to do is come up with three equations that we can use to solve for those three unknowns. First step, and there are several steps that we're going to go through as we go through this, but the first step, and I'm going to call this step 1. As we go through the problem, is we want to be able to find the Cartesian vector for each one of these forces. So step 1 is to develop the Cartesian vectors for each force. And that's going to be the first thing we want to do. So we want Cartesian vector notation for that. And so what this says is, I'm going to look at force FB. We know that one. I'll just write it as the quantities. So the vector force AB is equal to the magnitude of the force AB times the unit vector for AB. And we've already looked at that. That's basically the relationship between the vector quantity and the scalar quantity with the unit vector. So the scalar quantity times the unit vector gives us the Cartesian vector for that particular force system that you're looking at. So that is the step one, is we want to be able to write the Cartesian vectors. Okay, so let's do the Cartesian vector. Unit vector, first of all, for AB. We use this, and the only problem I'll ever give you is going to be the problem where it's going to be denoted using dimensions. I'm not going to use any angles between a force and a direction. I won't do that. This is typically, engineering drawings are dimensioned, and we're using this in three-dimensional space. It's much easier to get the unit vectors using dimensions, and that's the only type problem you'll see in here. So what we want is the I, J, and K components for each of the force vectors that we're looking at. And I'll go through one, and maybe you might go through two of them, and you can understand what we're doing. To give you a heads up then, okay, so here's the x-axis. The dimensions along the x-axis are going to be parallel to the x-axis. So here's a 2 meter here, parallel to the x-axis. That's going to be an x dimension. This is the y-axis. The y dimensions are going to be parallel to the y-axis. This is a y dimension here. Here's a y dimension. And in the z direction, k unit vector, it'll be parallel. The dimensions are going to be parallel to the z-axis. And here's a dimension parallel to the z-axis here, 6 meters. Okay, so that's it. You need to remember that as you're going through looking at how this works with the dimensions parallel to the axis systems that you're looking at. Okay. So let's look at the unit vector for AB. First thing we want to do is we're looking for the I component. Okay, so we're going from A to B. Here's B. We're looking for the I component. It's parallel to the x-axis, and it looks like it's this 2 meters. Here's the origin. Here's the end of that vector, AB. 2, and it's going in the positive x direction, so this is plus 2I. Okay, so it's going to be positive. We don't need to put a positive sign on that. So it's plus 2I. We want the J component that's in the y direction. The J component, and again, it's this 3 meter dimension here. And that's again positive. It's in the positive y-axis, so it's plus 3J. And in the z-axis or k direction, A to the origin, it's the 6 meters. And if you notice, the 6 meters is going negative y direction, so that's minus 6K. And then what we do to finish this is we divide by the square root of each of the IJK terms squared. So this is 2 squared plus 3 squared minus 6 squared. Okay. This value down here ends up being 7 as a denominator. So I can write UAB, unit vector AB, then is 2/7 I plus 3/7 J minus 6/7 K. And so that's the unit vector for AB. I'll come back Over here, now I want to write the Cartesian vector for FAB. So the Cartesian vector for FAB then is going to be the FAB as a scalar quantity, and we happen to know that value. That's the one value that's given. It's 700 newtons. So we write the scalar. So this is 700 times the unit vector, which is 2/7 I plus 3/7 J minus 6/7 K. And I multiply this out. 700 times each of those terms. This gives us 200I plus 300J minus 600K. Close that off, and the units are newtons. And so this ends up being what I call equation 1. Okay, that's for AB. I can do the same thing for A. Let me do one more for AC. We don't know what AC is. Okay, so let me do AC. So the unit vector for AC we'll get to that. So the unit vector for AC, again, we're looking at the XYZ components as we go through that. So A to C, looking along the x-axis, the x component that we're looking at is going to be what dimension? It looks like, and shows up the, you can't quite see the line. Here's the origin, here's C, and here's a dimension parallel to the x-axis. It's 1.5 meters. And again, that's going, if you look at it, that's going in what direction? Okay, going from A or from O to C. It looks like it's going in the negative direction, correct? Minus 1.5. So it's minus 1.5 I. The J dimension is what? Plus 2J. Okay. We're going plus 2 dimension, so it's plus 2J. And the K dimension is the same, it's the 6 meters down, and that's minus 6K. And again, we're going to divide by square root of 1.5 squared plus 2 squared minus 6 squared. And that denominator comes out to be 6.5. So that's 6.5 as a denominator. So UAC then is minus 1.5 over 6.5 I plus 2 over 6.5 J minus 6 over 6.5 K, and that's the unit vector. So the Cartesian vector FAC is equal to the scalar FAC, that'll be an unknown, times UAC. And so I can write this under here. FAC is going to be scalar FAC times this unit vector, which is 1.5 over 6.5 I plus 2 over 6.5 J minus 6 over 6.5 K. And then as a final step, we'll multiply this. So this will be FAC then. I'll multiply each of those terms by FAC. So this would be FAC. And again, I'm going to go ahead and do the 1.5 divided by 6.5 and so on as I go through that. This will be equal to, well, let me put it this number in front of these. You're going to multiply each one by FAC, but let me put this in front. So here, let me rewrite that. So it'll be consistent then. So FAC then, this 1.5 divided by 6.5 ends up being 0.2306. FAC. And then the next term, the J term, that's I, plus the J term then is J. Plus 0.3077, 0.3077 FAC, and then minus 0.931 FAC, and that is newtons. So I have two equations so far, the FAB equation and the FAC equation down here. Now I'm going to continue on with our notes. We'll follow the same procedure, and if you have this diagram in front of you, this you'll be able to see. I'm going to get the dimensions the same way for AB, AC, and AD. It's going to be the same thing. So AD we're going to get the same way. Okay, and get back to the notes on that. So let's stop share on that one. And then I'm going to share the screen here. Do that. Okay. So what we've done is we've found FAB. This is what we had for FAB. We did FAC. This is what we had for FAC. I'm going to do the same thing for FAD. Find the unit vectors. The I direction, if you look on there, is going to be +3. The J direction is -6, and the K dimension ends up being -6 also. Okay, divide by square root of 3 squared plus 6 squared minus 6 squared. And that denominator here is 3. So writing this is FAD. This will be 1/3 I minus 2/3 J minus 2/3 K. Now, if you'll notice, when I write the equation now, multiplying by each term by FAD, it's the same thing that we found FAC. All of a sudden, our unknown is going to appear in the IJK component. So FAD then is going to be, I'm going to multiply this out. 1/3 is 0.333 FADI. 2/3 is 0.667 FADJ. Minus 2/3 is 0.667 FADK. This is the third equation. So the first equation was the force in AB, and that was known. Then we do the force in AC and the force in AD. We'll put that the other force is just in the K direction. Okay, that's all it is. It's strictly K direction. Then we have the equilibrium conditions that we're going to look at. The vector force, Cartesian vector, is equal to the scalar quantity of F times the unit vector. We know that. Equilibrium says sum of forces equal to 0. And we have 4 forces. Force in AB plus the force in AC plus the force in AD plus F is equal to 0. So we have the 3 forces. They have to be equal to 0. And what I'm going to do is create the IJK components. So we have equation 1 up here, equation 2, and then equation 3. Okay, equation 1, which we developed, equation 2, which we developed, plus equation 3, which we developed. There's 2, there's 3, there's 1, plus the F. We haven't included that yet, equal to 0. And what that means is the vector quantities, AB, AC, and AD plus vector quantity F equals 0. And what I'm wanting to do is sum the I components in each of these. So 1, the I component, if I look at 1, is 200. Okay, there's 200. In equation 2, the I component in AC is 0.2308. And there's 0.2308. And then J component is 0.33308. 0. Again, these are all minus. And then I do the same thing with the j component. I add the j components together. And then I'm going to add all the k components together. And this is where the F force comes in. It's directed in the k direction. So I have 3 equations, ij and k. Okay, so here are the 3 components right here. I add all the I components together, so I go back to these 3 equations and pick out the I. Here's an I. And we'll go back to the equations. Yeah, 203 I. So we set the I, j, k components equal to 0. And these are the 3 equations that you need to solve the problem. Okay, we add the I equation is we take the I component from each of the equations, the j component from each of the equations, the k component from each of the equations. We set those equal to 0, and that satisfies our equation of equilibrium. And then what you do here is you can do this multiple ways, using substitution, whatever you want to do when you look at it. What I did is I took this j equation and solve for FAC, and to do that I just divide every term by 0.3077. So here's the j equation. So I divide every term by 0.3007, and what that does is that leaves me with FAC, okay, is equal to 21.17 FAD minus 0.975. Then I took this FAC and I put this back into equation I. So I went back to equation I, which is this equation. So I solved for FAC in terms of FAD, which means the only term I have here is FAD, which you see down here, my substituted, which is a very simple calculation to solve for FAD. Is equal to 510. And then I went back to this equation here. Once I had FAD, I put FAD back into this equation. I solved for FAC, 132 newtons. And then to get F, it's only in the K equation, and you needed FAC and FAD to do that. Well, I have the 2 values. I plug those values back in here, and I'm able to solve for F. And F is equal to 1,062 newtons. And this is where you need to be a little careful. We're only using 3 significant figures. And so this would be 1.06. And we moved it 3 places, which would be kilo. So it's 1.06 kilonewtons, Kn. And I'm saying that's all there is. I mean, it's quite a bit to a 3D problem. However, if you follow those steps, there's nothing difficult about it. You got to be careful. The only thing you can make a mistake on is getting a dimension incorrect, particularly with a sign, plus and minus, and getting the correct dimension. If you just remember the rule of being able to relate dimension along parallel to the axis. So if you're looking at an x dimension, that dimension will be parallel to the x-axis, or y dimension parallel to the y-axis, z dimension parallel to the z-axis. That's to get your ijk components. And I think that's what you would take a look at. So next week, we're going to start on force system resultants. That's chapter 4. I hope everyone was able to log into their eText finally. I worked Monday and Tuesday with 2 different consultants, 2 different firms. There's another firm involved other than Pearson, and they had some big issues. Pearson trying to get it to work, and the solution they had wasn't quite the solution that I wanted it to be in terms of access, but access is okay. And we worked it out the way that it's going to work in our system right now. So, and I'll be taking a look at what we can do in the textbook. So next week I'll post the assignment for chapter 3 today or tomorrow, and see you next week again for a Monday lecture and also the Wednesday lecture.